Stoichiometry. Say it with me. Stoichiometry. It's a weird word. It took me about a week to figure out how to say it correctly when I first learned this. But this is going to be our focus for at least today. So what this gets at is years ago when we started balancing equations, because let's face it, the last few weeks have felt like years, or months I should say. Those coefficients tell us something, right? We needed to balance equations in order to make sure that you had the same number of atoms on both sides, because this law of conservation of mass can't be violated. But that's because it gives us information. It tells us how these things come together. So if we look at this equation for the creation of water, the coefficient tells us that for every 2 molecules of water, or we can think of this in terms of moles, you need 1 oxygen molecule. And that's going to give us 2 water molecules. So those coefficients are much more, you can think of it as a recipe, is that it tells us how these things come together. That's supposed to say 2 moles of water glitch. Okay. And so we can use that to our advantage to figure out some other math, which is also fun. And that's kind of what stoichiometry is. It is using what is called the mole ratio from a balanced chemical equation. And that's one of the keys, is that it has to be balanced so that we know what the ratio actually is. And it allows us to convert from one compound to another. Right? If I know that it takes an oxygen molecule for every 2 hydrogens, then if I have, say, 10 hydrogens, I know how much oxygen I need. Or to think of like using a cooking analogy, if I know that I need, I don't know anything about cooking, if I need a pound of butter to make a cake, that seems like a lot of butter for a cake. So I apologize for any cooking fanatics out there. But if I need to make 10 cakes for a party, well, I know how much butter I need because I know what that ratio is. And that's what stoichiometry allows us to do in a chemical frame of reference. We do this kind of thing all the time, using ratios to figure out amounts. But stoichiometry is more of the chemistry version of that. Okay. So you are going to need this, which I believe was on the back of your pink sheets from before. I had you write all of this stuff down, and I think I just had the first 2. I think I just had you write down this one and this one. Maybe the other one. I think this was one that we added a little bit later when we started talking about gases, is that we have these things that allow us to convert from something we can observe in the real world, something we can observe in the lab, to the mole, right? We can observe mass. We can observe the volume of a gas. We can observe the volume of a solution and then use that concentration to figure out moles. So we have all of these little tiny gimmicks, these little tiny tools that allow us to convert from something into a mole, which is important because, again, the mole is becoming our gateway to figuring out information. So we're going to be using this. So let's look at an example, a simple example of going from moles to moles. So here I'm giving you 4.2 moles of hydrogen, and I want you to calculate how much oxygen is needed. So I'm converting from one compound, hydrogen, to a totally different compound in oxygen. So I'm going to need the mole ratio. And when I look at the equation, I can see that it takes 2 moles of hydrogen for every 1 mole of oxygen. Now, the way that I set this up, the way that I do this, is the exact same process we did in chapter 3 when we first started doing conversions. Step number 1 is write down what you have. So in the problem, you were given 4.2 moles of hydrogen. So write that down first, draw your X, and draw your line. Step number 2, look at the unit. The unit is going to tell you what goes on bottom because I want my units to cancel. So my 2 moles of hydrogen go on bottom, and that means my 1 mole of oxygen goes on top. And then I just solve. So my moles of hydrogen cancel out. So 4.2 times 1 divided by 2, I get an answer of 2.1 moles of oxygen. So you can kind of see why last term I was really harping on this is the way that I want you to solve these problems, because this is our process throughout this entire semester to be able to do these types of problems. We're just changing the tools that we're using, right? We're still building a house, but now I've given you different tools to be able to do that. So let's go ahead and try this one. I'll talk through it relatively slowly. So let's see, let you get a head start to see if you can solve it before I get to the end. So here it's the same equation, so it's going to be the same mole ratio, but instead we're looking at water. We're not looking at hydrogen, we're looking at water. So you want to make 0.57 moles of water. So how much oxygen do you need? So again, we're going from one compound, water, to a totally different compound in oxygen. So we need the mole ratio in order to do that. The mole ratio is 2 to 1. So for every 2 moles of water, you're going to need a mole of oxygen. To solve this, the first thing you do is write down what you're given, which in this case is the 0.57 moles of water. Next, I look at the unit to determine what's going to go on bottom, which is moles of water. So that goes on bottom so that it's going to cancel, which puts my 1 mole on top. I cancel my units and I solve. So 0.57 times 1 divided by 2 is going to give me an answer of 0.29 moles of oxygen. And that's really it. This is stoichiometry. Now, it does get more complex than this. And the only reason it actually doesn't get more complex, it's just the problems get longer because there's an issue that we have here. You don't measure moles in the lab. There's no way that we can do that, right? I don't have a scale that tells me the number of moles of a substance. And so we have to, this is the reason why we did chapter 3, is because we have to have a way to take the things that we can measure, like grams and liters, and figure out how to get them to a mole. So this is why we're going to be using, yes, we're just doing well, sometimes it's multiplication. It just depends on the unit. So this is why we need to know the molar mass, and why we're kind of, going back and doing those types of things all over again. Okay. So, hey, that was, where did it go? So what we're really adding here is we're taking something that we already know, and basically we're adding something right here in the middle, which is the mole ratio. So it's allowing us to bridge the gap here, to be able to take something that we can measure in the lab, convert it to moles, but then once we have that equation, we can now convert it to moles of anything in the equation. As long as we have the balanced chemical equation, I can take one piece of information about something, and I can now convert it to any information about anything in the problem. So this is why that mole is kind of the gatekeeper, and this stoichiometry really just opens the floodgates in terms of, right, if I know the mass of hydrogen, then that's all I need to know. That's going to get me to moles, and then once I'm at moles, I can figure out anything else that I want. So it's really quite magical in a lot of sense. So let's look at an example of going from moles to mass. So here I want to figure out how many grams of silver chloride will be made if I have 0.45 moles of silver nitrate. So I have two different compounds here. So when I know that I'm converting between compounds, I need the mole ratio. But I'm also trying to solve for grams. So that's going to tell me I'm going to need the molar mass as well. And since I only want grams of the silver chloride, that's what I need the molar mass for. So here's the mole ratio from the equation of silver nitrate to silver chloride. So 2 to 2, or a 1 to 1 ratio. And then the molar mass of silver chloride, because that's what I'm solving for, is 143.35. So I don't need the molar mass of silver nitrate, of calcium chloride. I don't need the molar mass of anything else, because I'm not converting to those things. So I only need the tools that I need for these substances that I have. So once we have the information, how do we do this? Step number 1, take what you're given in the problem, write it down. So I got my 0.45 moles of silver nitrate, because that's what's given to me in the problem. Draw your X, draw your line, and then look at the unit. So the unit is moles of silver nitrate, and so moles of silver nitrate, that's what's going to go on bottom. So then my moles of silver chloride go on top. Those units are going to cancel, and then I just continue playing the game. What's the next thing? Because I want grams. Well, this is moles of silver chloride. So what am I going to use? Moles of silver chloride. So now I'm going to use my molar mass. And so it's set up in a way so that all of my units cancel out. I'm left with grams of silver chloride is the only unit I have left, which is what I'm solving for. And so now I just do the math. So this is what I meant at the beginning, that this is really, it's just a math acrobatics. I'm just setting up this problem. I'm pairing out my units. to do the math. And so this 0.45, this was given in the problem. Right? Look up here in the problem, the 0.45 moles of silver nitrate. That's what I was given. So I don't do anything with the other substances because I don't need to, because the problem's not asking for that. So I'm only focusing on the things that I'm given in the problem and where I'm actually going. So then to do the math here, it's 0.45 times 2 divided by 2 times 143.35. And I get an answer of 65 grams. Let me clear my ink. So let's look at another example. So it's a mass to mass example. So the last one was moles to mass. This is mass to mass. So I want to know how many grams of barium hydroxide are made from 14 grams of sodium hydroxide. So I'm going from sodium hydroxide to barium hydroxide. So I'm going from one compound to a totally different compound. So I need the mole ratio to do that. So in this problem, my mole ratio is 2 to 1. So it takes 2 sodium hydroxides to make 1 barium hydroxide. And then the second thing that I notice is I'm starting at grams of sodium hydroxide. And I'm trying to calculate grams of barium hydroxide. So this is what tells me, the fact that I'm dealing in grams, that I need to know the molar mass of these two compounds. So I've already done that math for you. The molar mass of sodium hydroxide is 40. The molar mass of barium hydroxide is 171.35. I figured those out just by adding it up at the periodic table. So once I have all of my pieces, now it's solve my problem. So I take what I'm given, and what I'm given in the problem is the 14.5 grams of sodium hydroxide. So I write that down, I draw my X, I draw my line, and then it's just, I look at my units. So here is grams of sodium hydroxide. So which tool has grams of sodium hydroxide in it? Well, it's right here. It's my molar mass. So I'm going to use my molar mass to convert to moles. So because it's grams, that's what goes on bottom so that my units cancel. So those are going to cancel out. And now I have moles of sodium hydroxide. Well, which has moles of sodium hydroxide? It's not this. I just use that. Right? So here's my moles of sodium hydroxide. My mole ratio from the equation. So that's what I'm going to use next. I put the moles of NaOH on bottom. Why? So that it cancels out. And now I have moles of barium hydroxide. And so the last thing to use is the molar mass. I put moles of barium hydroxide on bottom. Why? So that it cancels. So everything cancels out, right? And then I just solve. To do this mathematically, it's going to be 14.5 divided by 40 divided by 2 and then times 171.35. All right, so if a number is on bottom, I divide by that number. If a number is on top, I multiply by that number. So there's a question on where did I get the 14.5? It's in the problem. Look in the blue oval at the top. The 14.5 is from the problem. So when I solve this, I get an answer of 31.1 grams of barium hydroxide. Let's look at this example. So how many molecules, so it's the same equation, but this time I want molecules of barium hydroxide, starting from the same amount, 14.5 grams of sodium hydroxide. So because it's the same two compounds, it's going to be the same mole ratio. I have grams of sodium hydroxide, so I need the molar mass. But for barium, it's molecules. Well, look on your pink sheet. What do we use to figure out molecules of something? Well, that was Avogadro's number. For every mole, there are 6.02 times 10 to the 23rd molecules. So this is virtually the exact same problem, the exact same setup, except I'm doing molecules of barium hydroxide instead of grams. So my setup is the same. What am I given in the problem? 14.5, so I'm going to write that down first. Sorry, my font color doesn't show up. That was not a wise choice. But then I just play my unit game. Grams of sodium hydroxide, that's what goes on bottom, so that it cancels. My mole ratio goes there. So if you look at this example compared to the last example, everything is the same except for that. That's the only thing that's different. And the reason it's different is because I want molecules instead of grams. And so then to do the math, it's 14.5 divided by 40 divided by 2 times 6.02 times 10 to the 23rd. And I get an answer of 1.09 times 10 to the 23rd molecules of barium hydroxide. Okay. There are a couple more examples here on the next few slides, which I think I'm going to skip for these notes. If you want to do them, and I would say I would highly suggest you do them. I'm just cutting it short just for time. I don't want to keep doing this for another 10 minutes. You can look at them in the video, or there's a hard copy of or a digital copy of these notes on Schoology that you can look at. But if you think about what we've been doing, this is kind of the setup here. Is right, that last example we did, we started here and we ended here. You started with grams of sodium hydroxide. What did we do? We used the molar mass to get to moles, and then we used the mole ratio to get to moles of barium hydroxide, and then we used Avogadro's number to get to molecules. And if you look at all of our other examples, this is our framework. This is how we have gone about solving these things.